For this video, we have section 4.5, which is a summary of curve sketching. And this is basically just a collection of all the stuff we've already done so far in chapter 4, and it's really very much a checklist section. And when I approach these problems, I always like to approach them in the same way, and that's dividing it up by how much calculus I have to do in order to sketch this curve. And the primary goal of this section is to get a better idea of what some certain functions are going to look like without the aid of a computer algebra system to graph it for us. So first up, we have precalculus, and these are things like finding the domain, x and y intercepts, and certain global shape properties about our function, and this can include symmetry and periodicity. So there are two kinds of symmetry. We can have even symmetry or odd symmetry, and these get their names from essentially polynomials. So a function is even if f of negative x is equal to f of regular x. This has the effect of being symmetric across the y-axis. And popular examples of these functions are going to be cosine of x, x squared. In fact, any even power of x, or any even power of some other symmetric function. So, for example, if I had sine of x quantity squared, or cosine of x quantity squared, those are both going to be even functions. And a function is odd if f of negative x is equal to the negative of f of regular x. And this is symmetry across the origin. The right side is the upside down version of the left side, or we could say that this is 180 degrees symmetric. The graph would look the same if I rotated it around 180 degrees. So examples of odd functions are x cubed, and in fact any odd power of x. Sine of x is an odd function. Tangent of x is an odd function. Tangent inverse is also an odd function, as well as something else like, say, 1 over x would also be an odd function. So let me just fill in a blurb about odd functions like I had for the even functions. Now, something neat about even and odd functions is how they interact with each other. If I have an even function plus an odd function, the result is incoherent. This will be a function which is neither even nor odd. But if I have even, we'll just use the letter e. If I have e multiplied by o, the result is going to be an odd function. If I have an even function times an even function, this will stay even. If I have an odd function times an odd function, this will become even. And similarly, the same thing works for division. If f of x is even, then 1 over f of x is even. And if f of x is odd, then 1 over f of x is odd. This is why 1 over x, for example, up here is included in the odd functions, because x, the line x, that's an odd function, and so 1 over x will also be odd. And we check these by comparing what happens when you plug in negative x. So if I had, for example, sine of x times cosine of x minus x squared, I would ask, is this an even function or an odd function? And I could either compare it using these guys up here, or I could plug in negative x to f, so I'll have an f of negative x, which is equal to sine of minus x, which is equal, multiplied by cosine of negative x minus negative x squared. And this turns out to sine of negative x, this is a property of sine, this is equal to negative sine of x. Cosine of negative x is just equal to regular cosine of x. And negative x quantity squared, the negatives will cancel, and I'll just have regular x squared again. So result from this one, this is not equal to negative 1 times f of x, since this is not an odd function. And this is not an even function because I have an extra negative out in the front here. But if I change this to, say, f of x equals sine of x times cosine of x minus x cubed, then it should be an odd function. since I'll have negative sine of regular x times cosine of regular x minus negative x to the power of 3. I'm going to have 3 negatives. 2 will cancel, and I'll still have an extra negative. So now I have plus x cubed here. And you'll notice this is equal to negative 1 times the original f of x. So this is an odd function because I have an odd function multiplied to an even function, and I'm subtracting an odd function. So as long as I keep odd functions together through addition and even functions together through addition, then nothing will change. And the only reason we bring this up is because whatever I get for critical points for the positive is going to correspond to critical points for the negative, which could potentially save us a little bit of effort and allow us to draw one half of the graph and determine what the other half looks like without ever checking that side at all. And the last thing we can check from pre-calculus is periodicity, if we were so interested in it. So a function is periodic, f of x is periodic if f of x plus n is equal to f of x for some n. We already know some periodic functions, for example sine and cosine. Sine and cosine are examples where n is equal to 2 pi. Tangent is an example where n is equal to pi, and whatever frequency modulation we have as a transformation inside of those is going to, of course, affect the period. And this can help us to graph larger sections of our problem if it's periodic, because we just have to check a small interval, however long the period is, and then we'll just copy it after that. But we typically won't be dealing with those because we're going to have the calculus problems. The second thing I can check after I have all the regular x-intercepts and domains and stuff like that is from our first derivative we get critical points where f prime of x is equal to 0 or f prime of x does not exist, and we use those like we did before to find local extrema. And we can use either the first derivative test where we do the number line thing, or the second derivative test where you take the second derivative and find out if it's concave up or down at that spot. But we can also go ahead and label off the first derivative intervals where the function is increasing or decreasing. We'd like to know where it's going up and where it's going down, because that's going to help us a lot for graphing our function without actually, checking 50 different points from -2 to 2. And after our first derivative, we have our second derivative. We have a second set of critical points where the derivative is equal to 0 or does not exist. And we use this to find points of inflection and intervals of concavity. And these help us to determine what kind of, how our function bends, if it's increasing or decreasing. So for example, if f prime of x is positive and f double prime of x is positive, my function is going to be curving upwards. It's moving upwards, and the rate at which it moves upwards is increasing. If f prime of x is less than 0, but the second derivative is still positive, then I'm going to have a curve which kind of flattens out. It's decreasing, but the slope of the tangent line is increasing, so it goes from pointing downwards and it tends towards a flatter line. If f prime of x is positive, but the second derivative is negative, that means I'll be increasing, but I'll be curving downwards, kind of like for natural log of x or the square root of x. My function is increasing, but the rate at which it's increasing decreases. So my slope starts off going up, and it tends towards flattening out. And last, if f prime of x is negative and f double prime of x is negative, then we have the last possible bending, where I'm decreasing and I get more negative in slope as I move along. Now these problems, of course, tend to have a lot of steps because we need to look for all of the classic culprits. So I'm not going to do too many by myself because this is technically a collection of all the work we've been doing in sections 4.1 through 4.3, where we found intervals of increasing, decreasing, and intervals of concavity. It's just now we're applying them and attempting to draw a better picture. So I'm going to do one of these, which is a complication of one which occurred on a previous exam. I'm going to use the function x squared times e to the x. Now I can start off finding all my pre-calculus information. I can find x and y intercepts. I can find x-intercepts if y is equal to 0, which means x squared times e to the x is equal to 0, which means since this is a product, either e to the x is equal to 0, that never happens because it's exponential, or x squared is equal to 0, which means x is equal to 0. And in contrast, if I wanted y-intercepts, that's if x is equal to 0, but I've already had that happen up here, and I'm only going to have one y-intercept, so I'm going to know that I'm going to have 0, 0 as part of my graph. I can follow this up by looking at the domain, but there are no problems with my domain. I'm never dividing by 0. I don't take the square roots of any negative numbers. I don't have a natural log function. There's really not much that can go wrong here. This domain is actually all real numbers. So I can move on to my first derivative, which is y prime equals, I have a product rule here, so I'm going to need x squared times e to the x plus 2x times e to the x, where if we remember the derivative of e to the x is just itself. And I want critical points, so I'll set this equal to 0, because just like the original function, the domain for this derivative is all real numbers. I have no problems of existence. So I'll set x squared e to the x plus 2x e to the x equal to 0. And I can factor off, it looks like an x times e to the x. So if I have x times e to the x, I'll be left with x plus 2. Which means I have two possible solutions for x. I have x equals 0 and x equals minus 2. Now if I want to check whether these critical numbers are maximum or minimum, I'll go ahead and add on here intervals of increasing and decreasing with that number line. So I have 0 and negative 2, and I'll test it at negative 3, negative 1. Let's emphasize that, and positive 1. So this could look a little ugly, so let's start with 1. F prime of 1 would be equal to, I'll use the factored version, x e to the x, 1 e to the 1 times 1 plus 2, but that is some positive number, looks like 3 times e. So I'm increasing after 0. F prime of negative 1 times e to the negative 1 times negative 1 plus 2 would give me, that's 1, negative e to the negative 1, which is negative 1 over e. It's a small number, but it is negative, so I'm negative here, so I'll be decreasing. Now I need to try at negative 3. Negative 3 e to the negative 3 times negative 3 plus 2. Looks like I'll have negative 3 times e to the minus 3 times negative 1. So this is actually 3 over e cubed. That's positive again. So I'm increasing here. So I could say I'm increasing from negative infinity up to my first critical point, and after my second critical point, so from 0 to infinity. And it's decreasing between the two, so from negative 2 to 0. Which coincidentally also tells us where my maxes and mins are. I'm going to have a local maximum here at negative 2 and a local minimum here at 0. So I have a local max at x equals negative 2 and a local min at x equals 0. And I think that's all I can get out of my first derivative, so I'll move on to the second derivative. And it looks like if I toss in product rule a couple more times, I've got x squared e to the x plus 2x e to the x for the first term, plus 2x e to the x, plus 2 times e to the x for the second term. And this simplifies a little bit. Silly. X squared e to the x plus 4x e to the x plus 2e to the x. And I want critical numbers from this again. I again don't have any problems with the domain for the second derivative because I just have x's and exponentials and I don't have any problems plugging in anything. So I'll just set it equal to 0. And again, I'm going to try to factor, looks like I can only factor e to the x out. So this is e to the x times x squared plus 4x plus 2. Well, the e to the x is never 0, which means I need to solve when this quadratic is equal to 0. But it doesn't look like I'll have an easy time factoring that, so I'll use the quadratic formula. I'll have x equals negative 4 plus or minus square root b squared, that's 4 squared minus 4 times 1 times 2, all over 2 times 1, which is negative 4 plus or minus the square root of 16 minus 8, all over 2. But since the square root of 8 would be equal to the square root of 2, or rather 2 times the square root of 2, this will be equal to negative 4 plus or minus 2 root 2. I can cancel these 2's and get negative 2 plus or minus root 2. Wouldn't be calculus if we didn't have some awful numbers. So what do we do with these? These are possible points of inflection. So what I would have to do is try to find out where my function is concave up and concave down. So how big is these numbers? Well, the square root of 2 is about 1.414 and change. So on a number line, I'm going to have 0 over here. I start at negative 2, negative 1, negative 3, and it looks like I'll have one critical point over here somewhere and another over here somewhere. So I'll use negative 4 and negative 1 and 0 to plug into my second derivative, and I'll use the factored form, e to the 0 times 0 squared plus 4 times 0 plus 2. E to the 0 power is equal to 1, so this is equal to 2, which that's positive. So this is concave up over here. F double prime of negative 1 would be e to the negative 1. Actually, this part out here, this e, is never going to be negative since it's exponential. But in here I'll have negative 1 squared plus 4 times negative 1 plus 2, which is, let's see, 1 over e times 1 minus 4 plus 2. That's a negative 1 in there, so this is negative 1 over e, which was negative. So this is concave down. And if I do this again with negative 4, I'll have e to the minus 4 squared plus 4 times minus 4 plus 2. So this is 1 over e to the 4th multiplied by, in here I'll have 16 plus a negative 16. So those are gone, plus 2, which looks like I have a positive number again. Which means both, I switched from positive to negative and negative to positive, which means both of my critical points here are actually points of inflection. But I don't think I'm going to be able to plug 2 plus or minus the square root of 2 into f of x and get something helpful. But let's add to this, because we can also investigate asymptotes. I didn't have any problems with my domain on this problem. I didn't have any vertical asymptotes, but I can still check for horizontal asymptotes. And this means I take limits to infinity. X to infinity of x squared e to the x. That's my function. But this is going to be infinity times infinity. It's just going to be a huge number. So no asymptote in that direction. But I should always check both directions because they can be different. But when I try to plug this in, the limit of e to the x as x goes to negative infinity is 0. So this is actually infinity times 0. And this is where section 4.4 comes in handy. I know how to deal with this indeterminate form because I have L'Hopital's rule. So I should pick one to flip down. I'm actually going to use the e to the x to go down because the derivative of e to the x is just itself. So as x goes to minus infinity, this is with no, not yet. I'm going to write x squared over 1 over e to the x. And that's the same thing as x squared over e to the minus x. I'll tell you now why I chose e to the x to flip down is because if I chose the x squared to flip down, the derivative of e to the x never changes. It's always just going to be e to the x. And so however many L'Hopital's rules I do, the e to the x will never go away. 1 over x squared, though, that has a derivative of negative 2 over x cubed. The power has increased. That's a situation where my L'Hopital's choice was bad because my problem is actually getting worse every time I use L'Hopital's. Versus what's going to happen with this problem, the way I've chosen it, if I do L'Hopital's on this, I'm going to get 2x all over negative e to the negative x, which is better because the power on my x has decreased. This is still going to look like infinity over infinity, but I know if I do one more L'Hopital's rule, it's all going to go away. And it is infinity over infinity because e to the negative infinity is e to the positive infinity. So one more, and I get 2 over negative positive e to the negative x. But this goes off to 2 over infinity positive, which is equal to 0. So I have a horizontal asymptote of 0 on the left side of my function, but I've got nothing helpful on the right side. It just blows up to infinity. If I try to draw what I've collected out of all of this, I had more negative information than I did positive. Let's go back to what we had. That's a lot of work. Nope, went too far. Here we are. I had x-intercepts of 0 and only 0. My critical points, I had a maximum at negative 2 and a minimum at 0. So f of negative 2, that's equal to negative 2 quantity squared e to the negative 2, which is 4 over e squared, whatever that is. F of 0, well, that's just, we already know what that is because that's my x-intercept. Great. Let's draw those. Here's my 0, 0. We'll have a 1, 2, 3. I know something happens here at negative 2, but this is an x-intercept and a local minimum. So that's going to happen. At negative 2, I had a local maximum, and it was 4 over e squared. But since e is bigger than 2, this is a number less than 1, so I'm just going to put it down here, and that was a local maximum. From the second derivative, I had information at negative 2 plus root 2, and over here at negative 2 minus root 2. These were changes in inflection, which means I was concave up afterwards. I was concave down here, up, and up. So since I'm down here, that means I go all the way over here, and then I kind of transition to flattening out. Here I go down, and then I transition to curving upwards. And I was curving upwards forever after that. I don't know exactly where any of these points are, but I can guess. And I know that out here towards the left, I had a horizontal asymptote. As x goes to negative infinity, my function went towards 0. These problems should really all work kind of more of the same from what was on the last test. We'll try to have a much faster turnaround so that we can have a chance to fix anything we might need to before we answer this problem and maybe get some free easy points. Next time we'll return to our ever lovely word problems with optimization.